So let me give you a chronological development of a frequency synthesizers, how to chase the performance phase wise. You know that in industry at least 30-40 people work in a group to develop this kind of work, and they take say 2 years plan for this. And there is a short loop run, there is a long, after 2-3 phases they finalize the design like that. So I'll give you some sort of a flavor like that, how from phase 1 development you get the interpretations of your results and change the design in the second phase, improve the performance further, go to the next phase and further, and then you will actually have the breakthrough. So that is a kind of case studies I will actually go now to design of a frequency synthesizer, how to chase the performance metrics and how to improve one by one looking at each modules. And I have already explained you the basics to understand this one. So coming into that, you know that for ZigBee or GSM or CDMA, whatever be your applications, the heart of any transceivers is these frequency synthesizers. And if you look at any frequency synthesizers which is at the middle of this, which drives both the mixers for up conversion and down conversions, and then after the mixer you have the filters, and the rest of the things is the A to D converter at 100 megahertz to 400 megahertz at 12 to 14 bit, and finally the DSP will conquer the world. So then the digital people will come and shake hands with the RF front end. But RF front end is omnipresent, right? You cannot avoid the front end designer. So that's why I say that, okay, you cannot avoid me because the front end will be required even you are making a digital assisted frequency synthesizers or RF front end. So coming into this, I am giving you what is the how to chase the design. You have to have some sort of a literature survey, right? For last say 10 years, you study that what are the various frequency synthesizers have been developed and what is the current status. Then you define your own target and chase it. Okay, let us fight. So look at here. In 2001, 0.35 micron technology, what are the basic parameters you have to chase? Channel spacing, all of you know that in GSM it is 1 megahertz. Frequency range is 2.4 to 2.5 gigahertz, so 100 channels. Loop filter is off chip. At that time, loop filters is always off chip. And then you have a kind of a phase noise is 116 dBc hertz at 2 megahertz offset, and reference power which is 53 dBc. You might recall my first VCO design, I have shown you some kink at the left and right side of the center frequency, which will basically at 5 megahertz spacing of our reference frequency, that is known as the sparse. And the sparse are very bad because they will cause some sort of intermodulations products, and so you have to remove the sparse. 53 dBc is not a very good spar performance. And the settling time. Settling time is an important issue because the frequency synthesizer is synthesizing from the lowest end of your frequency to the highest end and again go back. So now suppose you are transmitting me the channel 1, you are transmitting to channel 2 and so on, channel 100. And the frequency synthesizer is hopping from channel 1, if they get some signal locked in, get the modulated signal extracted out of it, going to the channel 2 like that. The same frequency synthesizer is working. Then what will be the time required for hopping? Suppose your data bit rate is 1 Mbps kind of things. So you need a settling time at least few microseconds. In case of ZigBee, the typical 16 channel, the kind of settling time means what? That is your PLL is locked in say at lower frequency 2.4 or at higher frequency 2.48, suddenly then it goes back to 2.4. You are clear? So you are going from the left end of your frequency spectrum, going to the extreme right hand to the 2.48, then you go back to 2.4. Then transition of your lock-in from 2.48 gigahertz to 2.4, the time required is called the settling time. And if the settling time is much faster than your data transmission rate, then all the channels will look like as a stationary, as if there is only one channel in front of you. I am very fast changing my torch. So as if from your side, my transmitter or my receiver is always on, because I am changing it very fast. By using like a, that perception of visions, the frame is changing very fast, looks like a steady state. Like a frequency synthesizer, I am hopping the frequency in a very fast. So the settling time that determines that. Okay, so higher the frame rate or higher the hopping frequency, you should have less settling time. How much? I said for Zigbee, it is 120 microseconds. Like this, if you look at here, another very important thing is the power consumptions. So power consumptions and the phase noise. Okay. So if you look at, you can always demand a very high phase noise, but look at the power consumptions. 14 milliwatt at 1 volt, where they have getting 115.9 dVc hertz, say at 0.25, that is also simulation result and so on. If it is a Zigbee, 3.48 milliwatt, and that the dBc hertz, so always you find, if you look at, scan through it, that your phase noise performance is actually is a trade-off between the power consumptions and the phase noise. Always, if you burn more current, you will always get better phase noise, because actually you are adding more power to your signals. That's where your phase noise is getting improved. These are pseudo developments. And if you look at the 2014 and so on, remember that it has got simulation result, not the test result, minus 130, but look at its power consumptions. 9 milliwatt of power, that gives me 130 dBc hertz, that too in a simulation result in 2014 at a frequency, this is for Bluetooth, that is at 2.4 gig. So with this, let me give you this, what kind of specifications you should start with. So I say this for Zigbee applications. So my divider is, I will be using an integer mode, because my spacing is 5 megahertz. So 480, 481 up to 495, that is good enough for my 16 channels. Clear? But look at here, if you design the frequency synthesizer for your TV tuner. If a TV tuner, there is a problem that you have a frequency for 426 to 600 something, 70, and there are more than 200 channels. The channel spacing is not limited to the integer mode, then you have to actually divide it by fraction. That means if you have gigahertz, integer mode give you the megahertz kind of spacing. Clear? Now you need kilohertz, therefore you go for the fraction. That means your divider will be now n plus 1 by n. So that 1 by n, say 10 or 5, suppose 480, then it next is the 481 in case of integer mode frequency synthesizer. In case of fractional, it will be 480.1, 480.2, and that way you will go to 481, then 481.1, like that. So you will all get the fractional frequency that will cater to the need of these 200 plus channels of a TV tuner of any frequency synthesizers within the range of 400 to 670 megahertz. So that is known as the fractional n frequency synthesizers. So here I am restricted to the development of integer n frequency synthesizer, because my channel is limited to 70, 80 or 16 in this case. Clear? So where you will choose n type, that is integer mode, where you choose the fractional n. Clear? Now the channel spacing is 5 megahertz and the settling time is less than 192 microseconds. That is the requirement when the data bit rate is within 1 Mbps following the Zigbee. Now coming into this is the standard architecture. So I am not going to, I have to design the PFT, the charge pump, the loop filters, VCO and the divider. And the divider would have a 6-bit control, okay, so that its division ratio changes from say 480 to 495. Now coming into this, let me give you two important aspects. Since I have gone into the VCO design quite details, then I should give you actual design what you should do in making a frequency synthesizer working, beating some commercial values. So what you have to do that your KVCO, that is delta f by delta v, okay, there is a finite frequency tuning range, and for a this kind of 2.4 to 2.48 you can easily calculate it is less than 5% of your center frequency. And then how you are doing it? Now you are actually having a control voltage from the charge pump which is going to your VCO and changing the frequency, and there is a 4-bit control that is changing the switch capacitors, and accordingly bands are getting selected. So that is the VCO, but top of that, if you have been asked to change the tuning range further, then I am giving you a modified circuit approach which is pretty simple to do that, is introduction. So you know this part you have already taught. So this is a complementary cross coupled LC VCO with bank of switch capacitors, and this is a tail current generator, and where the charge pump output, that is the filter output from the frequency synthesizer block, is fed to a common source amplifier, and then it goes to a capacitor, and this capacitor is actually used because if there is a VDD and there is some kind of a transient, it is called the supply bounds or the ground bounds, some transient might cause from the VDT, so that might go into your varactor and that can cause the frequency fluctuations. To avoid it, what you have done, you have used a capacitors so that the large transients can go to ground. And this is the improvement, that is this, you can actually have more control voltage to your varactor gate because you have a common source stage in between. So that is one such developments. Let us come to that varactor bias, the reported work say that it is consuming bias circuit is 1.23 milliampere, and in our case it is 40 microampere, and the reference source, that means your mirror, current mirror produces 100 microampere of current. So kind of current mirror design, you understand that you are consuming basically 40 microampere, but it should be capable of developing this 100 microampere. Now if you increase the tuning range, then what is the advantage to that I am saying. So suppose this is with the MOS varactor tuning without that common source stage. How would you say that? This is the control voltage, this is the frequency, is like that. So this is a very steep del V del C, clear? It is a steep one. So now if you have that common source stage, then what is happening? It becomes little sluggish. So your slope is less, that means KVCO is less. If KVCO is less, that means your noise performance would have been better. So there is a small changes you made in your conventional cross coupled LC coupled oscillators to that. So that is the KVCO without the MOS, without this stage, and this is with that common source stage, that improves much less KVCO, where it goes to 150 or 60 kind of megahertz per volt, but the maximum it goes to around 70 megahertz per volt just by introducing a common source stage. Okay, this is the first alternations. So that is the linearity of the control voltage has been increased by more than twice. Simple, just this voltage follower, source follower. Next one, that I have one VCO, but why I will go for single VCO? I can have those VCOs in parallel. So multiple VCOs can also widen my tuning range, because I want to have a wide band kind of a tuning range. So that is another changes has been carried out in the design to chase my target. So look at here, this is the PMOS pair and the NMOS pair, and in between there are 6 or 5 VCO depending upon your requirements, but these are all the parallel cascading of this MOS varactors, and each of them is biased by this biasing circuits, okay, and then the control voltage is going to those VCOs and to the varactors in these fashions, and then along with the band select filters, which is switch capacitors arrays, then you find that the KVCO is, each of them is 30 megahertz per volt, and you can have a 2.5 nanohenry inductor, and here you have used IE3D to design the layout of this inductor and to find out its number of turns and its quality factors and so on. So, look at here what happens. If you have the frequency versus voltage, then you will understand this is the tuning range of the first varactor, this is the tuning characteristic of the second varactor, this is the third one and fourth one and fifth one. So, if you add all of them, then finally you will have a very huge tuning range, which is called the resultant tuning range of your oscillations or KVCO. So, in this way, if you look at the KVCO, so you have KVCO almost down to close to 0, you understand. Single KVCO, they is the same thing. I have one varactor, I have been given a task, for example, to tune say 100 megahertz. So, whatever my voltage, it is not going below my threshold voltage. So, maximum delta V available is say 0.2 volt, and I have 100 megahertz. So, 0.2 volt 100 means 200 KVCO. Here it is roughly like 150 megahertz per volt. Clear? Now, I am giving the task to 5 or 6 such varactor, and they are adding. So, all the capacitors are being added in parallel and they are varying. In that case, what will happen? Each will have tune and next one will tune like that. So, immediately you will have a continuous tuning range, the wider tuning range, where KVCO will be much lower. That you are seeing from that signal that you have less, because my target is to low power consumptions and improve the phase noise performance. So, we have introduced arrays of such varactors to reduce the KVCO. Clear? So, you are finding out that using this conventional MOS varactor, your KVCO becoming minus 150, whereas using this cascaded multiple varactor, your KVCO is becoming around 25 like that. Now, this is the measured one. So, if you look at the measured one, using this conventional MOS varactor simulated, and this is the tested. So, look at here, using distributed bias MOS varactor, say 5 such varactor, this is your KVCO. Okay? And whereas conventional one, the KVCO is much higher. Do not look at the sign, but look at the magnitude. So, you are having much less KVCO, close to 0 or something 20 like that, when you have a distributed MOS varactors, and these are simulation results and this is the measured results. So, the concepts that has now been coming into the silicon results. So, with this background, let us go into our specification once more. So, what is there? You have a literature survey, you have a previous work. So, we found that 2.4 to 2.4 gigahertz is my frequency of range, 16 channel 5 megahertz, and phase noise whatever I will accept, settling time is 192, that is the coming from the protocol. But now you said that I want to consume less than 10 milliwatt of power, and at least I have minus 110 dB C hertz at 1 megahertz offset with reference part 60 dB and settling time less than 50 microseconds. So, mind it, my requirement was 190 microseconds, but I have given it 50 microseconds because of the parasitic. The parasitic model may not be that accurate, so I have to make the design little bit of much more cautious design. So, make it say 1/3 of that I have tried to achieve. Let me see what we can achieve in the silicon. So, with this, let me go to the first phase of the frequency synthesizer design, because we have already designed the VCO, we have made some progress in it. So, this is the reference signal which is coming from a 5 megahertz crystal oscillators. That provides me the input reference frequency, and going to the PFD, I mentioned how the PFD works. Then it is going to the charge pump and the loop filters. Remember, the charge pump and the loop filters will be the same unit, because the capacitors is finally gets charged with that constant current source modulated by the charge pump, and that's fed to the control voltage of the VCO, and the VCO is now being fed to the programmable divider, and this programmable divider is controlled by a 6-bit word, and that also goes to the VCO to control the VCO. So, say 4-bit, 2-bit, like that, 4-bit you will go for the VCO switch capacitor architecture, and 2-bit for the programmable divider, depending upon how you make your word count at the digital logic array. And then you remember that after that we fed it to the PFD after its division. Suppose 2.4 gigahertz is free running frequency of the oscillator, and the divider at this moment is 480, then 5 megahertz will come and it will compare with this reference frequency. Now you are finding two different things. One is the charge pump loop filter, and other one is the programmable divider. There the reference generator, that means the bias generator, we have introducing some sort of external control. So, there is an external pin where you can introduce some current, inject some current, so that the bias voltage generator can be tuned, fine tuned, so that any kind of current mismatch in the charge pump can be adjusted. Because I said that when it is up count or down count, then you find the top transistor is on, and that is charging my capacitors, and when it is down, that is the phase is lagging, then the lower transistor is on, capacitor is discharged through this path. So, if there is a up current and the down current, there is a mismatch, that will cause a permanent offset in the phase, and that will cause harm to your lock-in characteristics. Therefore, you need fine tuning to avoid this mismatch. There is some sort of controllability has been introduced in this bias control generator. How? Because you introduce some extra current to compensate that variations. Then another thing you have introduced, that I want to test my loop within closed loop or open loop. Therefore, the free running frequency, that is I want to check only the VCO frequency. I am not going interested about the divider one only. So, what we have done, look at this pink line. So, that yellow line and the pink line, the differential one, goes to a buffer, then finally fed to the output. So, that is the output pin, that is your ground SGS, that is you have a ground in between and source ground signal SGS kind of thumb, so that you can get the differential output or the signal. You need three such two pairs of that to find out this frequency. So, that is you need a buffer to isolate the free running VCO frequency from the loading from outside. And whenever you try to get, suppose I want to see the programmable divider output, you need a buffer, and this is the division output 5 megahertz. So, make it in your chip that these two blocks and these blocks controlled one is the apart deviation from the conventional design approach to avoid the loading. So, now coming to this building blocks of the VCO, I have already talked about how we do control the switch capacitors and so on, and this linear control voltage and making this device. This is the schematic of that. And then how we do calculate the KVCO, that is I am giving you a short calculations you can look at in your leisure time, that suppose the control voltage is V control range and KVCO. So, what I said that you have to calculate from the threshold voltage of your transistors and in the linear region. So, if you look at the KVCO, so you do not have much options, because your transistors going from the accumulation region to the so suppose this is a very interesting thing. So, this is the region where you have the linearity one. So, this is your V and this is your C by C aux. So, this is the accumulation region, then the inversion and then the deep inversion. So, this is your VTH. So, I say that you have the linear region here. So, if you take the slope of here, that is your delta F, delta V, and that is your delta C, and that delta V and delta C we introduces the corresponding change in the frequency. Okay? So, that is, this is the linear region, and if you look at this delta V, suppose it is 0.Vth is equal to 0.6 volt and suppose 0. So, this region may be 0.2 and 0.4. So, this is delta V. So, if you look at KVCO, so how would you calculate your KVCO? Now, what is the F range and what is the F margin? That is, what is the margin in between two channels you will introduce. For example, my range is 75 megahertz and a linear control, that is 0.9 volt up to that, assuming that is a 40 megahertz is the margin, then you can use this formula to find out the KVCO is 172 megahertz, which is very, very high. So, you have to again recalculate. Then this F range, how will you recalculate? Then you are giving you that concept, that in spite of tuning it to a wide range of 75 megahertz, then I can make subbands. So, that subbands of 10 megahertz, immediately there are 8 such subbands of say 10 megahertz spacing, and then your KVCO can be limited to 60 megahertz. Clear? So, only you have introduced this change in the F range, because now switch capacitors is taking you from the frequency band 1 to frequency band 2 or 3. Then when you reach the frequency band 2 or 3, then you vary the frequency by this delta V, so that you can actually extract the signals out of your carrier. Clear? So, KVCO has been reduced by subband architectures. So, this is the pictorial vision of that. What you have done? You have made 8 such band, and then you are varying this capacitance control voltage to vary the frequency. So, this is your SCF in on, then you have to go to the highest frequency, you are varying, so that in your VCO design we have explained. So, that is the VCO part. Next part is that divider. So, divider you can make either divide by 2 or divide by 3. Then the divider will be cascaded, and you can find there is 8 such cell has been given, and combination of this divide by 2 and divide by 3 will introduce the division ratio from 480 to 495. Then you have to make some sort of calculations that m number of cells is divided by 2 and rest of the cells, say total cell is A. So, m into the number of cell n plus total number of cell A minus m into that ratio, that is divided by 3, is the total effective division ratios. So, that you can program, that is up to your choice. You might make some sort of approach to make it simpler. But one of the major concerns of divider design, which I thought of, because suppose your divider is seeing here how much, this is coming from your VCO. What is the frequency? 2.4 gigahertz. Suppose it is say 2 divided by 2, what is the frequency here? It is 1.2 gigahertz. Then what will be the frequency here? It is 600 megahertz. So, divide by 2, if is 2 are there, then you are having from 2.4 gigahertz to 600 megahertz. But this one is seeing a very huge frequency, and when there is a huge frequency, you know, power consumption will be high. Then what kind of logic system you will be using? That is point. Whether you will go for a static logic systems or you will go for a CML, you have to make a very judicious selection. A CML is a faster logic, but it will have a cost of power. Power budget will be high, whereas the static logic is low power but little slower. So, what is the choice? That the first 2 cells or 3 cells I will go for the CML logic, and rest of the cell I can go to the static one. So, that here my frequency is 600 megahertz. My assumption is that static logic will work at magic figure 674 megahertz. So, I said that okay, after 600 megahertz you go for the static logic, but before that you need faster response, it will not work the standard CMOS. So, you will go for this is 180 nanometer kind of realizations at the time. So, we go for this. So, you understand the divider, you choose first what will be the pattern of divide by 2 and divide by 3, how many cells will divide by 2 and how many cells will be divided by 3. Then the frontal divider would be implemented by current mode logics, because it is faster logic systems. Okay. I have a detailed idea how to make the power delay product or jitter delay product less than that I am not coming at this moment. Now, I said that how to solve this problem. This is the PFD. So, you have the up and the down. So, when both are 1, that means when both are 1, up and down are 1, that is the lock conditions. Then there is a delay in it, so that the D flip flop gets reset. That if you do not introduce the delay, then what will happen? That time when both are on, your charge pump will actually be undecided. So, to avoid that uncertainty, you have introduced a delay which will introduce some kind of a dead zone. Definitely you will sacrifice some delta phi phase difference. Within the error, it is assumed to be right. Then you are using some kind of this delay circuit has been realized by this kind of a buffer. You are introducing a transmission gate to realize the delay. Clear? So, this is the PFD design, where you have this up and down pulse to turn on your current source, where you have used some kind of a delay to avoid the dead zone problem. Now, what is this? This is, I have already mentioned that when it is locked in, then almost the PFD input and x and y, one is coming from the reference frequency and other is coming from the divider, are more or less matched, but little bit of difference in the mismatch of the up and down current has been shown over here. And then how this triggering voltage for the up side, this is the up complementary side and this is the down side, is like that to trigger the current source to turn on its current to charge the capacitor. So, these are the kind of systems under locked conditions. So, under locked condition, you are seeing that both the reference frequency and the divider frequency are matched, but there is a fine difference because of the charge pump current difference. Now, this is the building block of the charge pump and the loop filters. You always make, this is the loop filter design and this is the charge pump, and you know that this is the up bit and this is the down bit. We turn on this transistors MD, M3 and this MS1, and that is being compared with comparators, and finally it actually gives you a power pulse width modulated, or I would say the duration of the pulse to turn on this capacitor charging depending upon what the duration of the phase lag. So, this is the current current bearing bias circuits. So, this is how you make that lock in. So, you find that this in the lock, then the amplitude is very sharp, that is change in these things and this capacitor getting charged. So, you are getting the capacitor charge, then is again in like that. So, capacitor is being charged in these fashions, and how the profile, this is the control voltage profile which is going to your VCO. So, with this, let us look at our first design. So, this is the it is a 180 nanometer one. So, look at here, this is the kind of inductor, and this is the VCO, divider, bias generators and so on, and this is a complete chip on the top of the PCB. So, you will make that PCB inside. This is a relatively new one which I have shown in earlier was lower, and then we go for the measurement of the phase noise. Look at the phase noise. I found that this is the phase noise characteristics, actual data from the network analyzer having a special module, and this is the phase noise, and then finally it is coming down, and this is the thermal noise. So, this is the thermal noise floor and this is the phase noise 1 by f noise, right, and this is the bandwidth, this is the width band and out of band. So, if you look at 1 megahertz, then you will find that at 1 megahertz the phase noise, spot noise is 70.3. I will summarize that one, just 2 minutes wait. Then, and if you look at the spectrum, okay, then what I am saying that apart from the phase noise, we found in the design, this is the actual data, this is the spectrum. These are after 5 megahertz spacing and 10 megahertz, 2 times of the reference frequency, these are the reference parts. And so, this is the fundamentals, say at 2.4 and like that, and this is actually the performance is minus 40.84 dBc, this part. So, that is not a good design, right, because my design should have at least 60 dB difference. So, I found Okay, let us go to the next phase of the design. And also the phase noise performance is not that good. So, let me go to the next design. So, that is the performance summary. What I am expected, I want to use it 1.8 volt. I am using the 0.18 micron digital CMOS process because it is a vanilla process. I have to integrate my digital chip inside. So, I got integer n and it consumes 7.95 milliwatt. At least I have been able to restrict the power consumption within the limited, within my limits. Frequency is fine, but you know that phase noise performance I was targeting 120, but I am getting 108 at 1 megahertz offset. So, I have to improve, right? And I want 60 dB reference part, but I get only 40.84 dBc. And also settling time pretty good. I got 25 microseconds, and the millimeter, that is the die area, is 0.4875 millimeter square, and the division ratio is 480 to 496. And all the chips you can see from the die is purely on chip. So, this is a very interesting work being referred many times, because it is a completely on chip frequency synthesizer. None of the components are outside, including the loop filters. Okay? This is the first design, is a fully on chip frequency synthesizer for Zigbee applications. But I am not happy. I want to improve my spurs further down and to improve the phase noise performance. So, next phase of the design, I make my next, this is the measured result. So, you have to improve your design further in the second phase. Let us make a target. I got from 10 milliwatt, I got 7.95. Why not we target less than 5 milliwatt? And the kind of phase noise performance is 120 and 3 megahertz 130, and reference point is 60 dB. Since I got an advantage in my settling time of 50 microsecond, why don't you target 20 microseconds? So, this way you are increasing your own benchmark to improve the performance. So, here there is some things which require little bit of study. The first thing I found that the major phase noise contributions coming from your VCO, this is one. Secondly, I have used a 5 megahertz reference clock. And if I look the data sheet, then this clock 5 megahertz that contributing noise to the systems, and if you go to the higher frequency clock, that is have much better frequency tolerance, that is change in the frequency because of the temperature variation or their noise contribution minded for any oscillator. If you buy the oscillators from market, then a 5 megahertz or 10 megahertz or 20 megahertz, which one you will select? You will always select little higher megahertz. That will give a better noise characteristics than the lower frequency. So, what I have done, in spite of 5 megahertz, I have used 10 megahertz, and then similarly I have this charge pump loop filters having the current control and programmable divider and so on. So, some few internal changes have been carried. So, it is a divide by 2 because my reference frequency is 5 megahertz, but I am getting 10 megahertz crystals internally divide by 2, I make 5 megahertz to improve my noise, to reduce the noise contributed from my clock. And then we look into the capacitors, and this again he used this frequency tuning techniques with multiple varactors and so on. And then finally, this is the, in spite of this low pass filter passive, we have used some sort of an active low pass filters to reduce the performance characteristics, and then the next phase of the design. So, if you look at here, this is the completely fully on chip frequency synthesizers, and with the inductor and so on, and this is the divider and the buffer. So, you understand all your anti-gain buffer, the band gap, the PFD and charge pump in one side, and the capacitance block. This is a complete die micrograph. Clear? So, this is how you are improving the performance from one side step by step. Then coming to the phase noise performance. So, this is the phase noise. We found the data that at 1 megahertz I got 115.76 dBc, okay, where in-band noise is 54.58 dBc hertz. So, if you look at here that at 1 megahertz offset, minus 115 dBc hertz. So my target is simply minus 120 megahertz. So still I have to go.
So sorry to interrupt.
I have to go again to this. So now, if you look at the sparse, because I have to play with my sparse. So if you look at the sparse, you will remember that initially it was 40 dB, but now the sparse had been reduced to 68.62. So what was the target? 60 dB. So now, you know that sparse, power consumptions and the phase noise, both are the three interdependent characters. So you have to actually push your circuits to get your target specs. So now the sparse is within the acceptance level. So if you like summarize, and this is the settling time, that is from the lowest frequency to the highest frequency, how much time it required. Now it is locked in at the lower frequency, and then it again goes back to the higher frequency, how much time is required to lock in. So it is 53.17 microseconds. So that is the settling time. So now if you can summarize the results, then the supply voltage has been to 1.5 volt, and there is a restriction. You are using AP digital CMOS process. In AP digital CMOS process, your AP layer is doped. That means your quality factor is within 3 to 4. So your phase noise performance cannot be that good. And again, you are using power consumption. You can always have better phase noise performance, but I have restricted the power consumption even less than 5 milliwatt. Look at the power consumption of this new design. Is fabricated and silicon data is 4.7 milliwatt. Okay, perhaps that time it was the lowest one. And then you have a reference frequency is 10 megahertz, channel spacing 5 megahertz, and we got 115 dBc hertz with phase noise performance, and this is the settling time and so on. So settling time I am not that worried about, because in a ZigBee the kind of settling time for protocol is more than 120 microseconds. So 53 would have been no problem. So still miles to go. I have to improve my phase noise performance even better. How to do that? So before that, let me go to the die micrograph. So this is the various buffer and the band gap and VCO and the dividers, okay, channel blocks like this. This is the die micrograph. And then you will have this IIT KGP chip on the populated board and the back side of that. So you can take the signals from outside. Okay, that is the ground pin. Okay, so copper thickness is minimum 35, and you can use FR4 board for high frequency circuits. And then coming into the testing part. So this is my old test lab. Now it has been changed completely. So you can see yourself that the spectrum coming from the spectrum analyzer, and this is you can use an FPGA board to control this control bit pattern to actually make 6-bit or 8-bit pattern, okay, to make that switch capacitor arrays and the control bit of your divider. So both can be programmed by this one, and this is the power supply and so on, and this is the test board. But what I said that I actually having a 9-volt battery divided by some voltage divider, because the line noise sometimes disturb in your measurement of noise and signals. So you can use a battery. Okay, and if you have I am going to have a Faraday cage and line filters like that, but later on at that time we have used a battery to power on my chip, so that no line noise comes to the systems. So battery is used. Now coming into this, I have another miles to go. So you find that whatever be the literature review I made, then technology is okay, fine. I have done all kind of tailoring with the circuits, all kind of pushing the limits of the circuit performance because I have a constrained process. I am working with 180 nanometer digital CMOS process to make the cost of the chip much lower. But my desire is to make this phase noise performance less than minus 120 dBc at 1 megahertz offset, that too by consuming less than 5 milliwatt power. It is not an easy task. Whoever be the circuit designer, they understand the problem, because you can always burn more current, better phase noise performance. but you have a restricted power consumptions, but you need your phase noise there. Then I think, why not we go into the physics of it and find out that which are the problem of introducing the improvement in the phase noise performance. Then I found phase noise performance is inversely proportional to the square of the Q. And I mentioned many times that the main problem is two. One is your LC tank, that is the 78% noise being contributed by this VCO. And that contribution is primarily from the limited quality factor of your inductor and the capacitors. So can you think of a new technology itself, a quantum jump, a new breakthrough? So then we thought of, let's make an inductor which is lying on the top of my 6th or 7th metal layers, depending upon what process, okay? And then you make it hanging. And if you hang it, then you can reduce the eddy current loss, so you can improve this quality factor. So that's the structure, right? What we have done, you can see yourself. So this is the hanging inductor, and this is the 130 nanometer CMOS circuits, and this is connected through bond wires. Okay? And this is connected through bond wires. So how the bond wires has to be connected, what will be the length, what will be the shape of this. This is a very, very critical things. So I published the device part of that work in TED, Transaction on Electron Device, and the circuit part is published in IEEE MTT. And you find itself, I don't have to tell, look at the spectrum. Just look at the spectrum. No spark and almost ground. So look at the phase noise performance. If I summarize this one, this is the quality factor, and this is the change in the current density. Look at here. I compare with all the results till date. Look at this work. The phase noise performance is unbeatable. Minus 138.8 dBc at 1 megahertz offset, which is a world record till now, published in 2015 in IEEE. So think of it that here lies the catch, that where you have to start your journey from the conventional circuit to some unconventional thinking. So that is the thing you have to put in your in your research career or your students, how to motivate that one. After that, I try to think, you have some time? How much time I have? Huh? 1 hour. So then I thought, okay, I worked with capacitors and changed my phase noise performance. What next? Next, I thought of, let me capacitors get something else. Then I quickly go into next 15 minutes that I can have those capacitors, 2 parallel plates, okay? Mechanical, because earlier days you have those, normally in a TV, we are old people, so we used to have gang capacitors, right? Remember, metal one? Changing the overlapping gap, you can find the tune this. So that is a mechanical. So that capacitors being an on-chip, can we make a mechanical capacitors, miniaturized capacitors, and that quality factor will be much better? So with this vision, we try to develop something that is called a MEMS-based varactors. So idea is that you have 2 parallel plates, and if you apply the voltage, then this parallel plate will be pulled down. So once it's pulled down, then what will happen? The change in capacitance would occur. So by applying the voltage, you can actually change the capacitor. Same way it is acting as a varactor, but it is a mechanical varactor, which is having much better quality factor because power dissipation is almost nil. It is a mechanical tuner. So once you make that one, I am quickly going, then this is the frequency tuning characteristics. I found that this, you cannot increase the voltage of your varactor, like here you have a VTH is the maximum limits of that, In this parallel plate capacitor, the maximum limit is the pull-in voltage. If you apply the voltage beyond that, then the top plate will actually collapse on the bottom place. That is called the pull-in phenomena. Very simple thing. Suppose two parallel plates, okay. So you are applied a voltage. So it will, what will happen? If one of the bottom plate is fixed, the top plate is movable, then the top plate will be moving down, okay. Once it moves down, then your gap changes, capacitance will go up, sure. Now, if the voltage I increase, okay, gap is going down, the capacitance is increasing. If the capacitor is increasing, then your more energy is coming, so more force will come, so more it will be attracted towards the bottom plate. Again the capacitance will go down, again the gap is going down, more force will be there, and finally it is some kind of a positive feedback. So if it is a positive feedback, then essentially what is the outcome of that? That after some time you will find the capacitance does not have enough restoring force to have a constant gap, it will go to the unstable state, and finally the electrostatic force will pull it down and your capacitors will simply be shorted to the ground. And that voltage, which is that critical voltage when your effective spring constant is equal to 0, is called the pull-in voltage. In that case, MOS varactor, you have the threshold voltage. In case of a mechanical tuner, you have this pull-in voltage. So pull-in voltage is the maximum voltage you can go. So if I look at here, this is the voltage versus the maximum capacitance. You will find with the voltage the gap is decreasing and I am getting that change in the frequency, and at that time it is shorted, so I am not getting any kind of capacitance out of it. So with this, let me go that I introduce this varactor replaced with a MEMS based capacitors. So in this way you find there is a very interesting thing, that in case of this f equal to 1 by twice by root over LC, so in that case, you know, these kinds of MEMS varactor, maximum change in capacitance would occur is 1.5, because pull-in voltage, what I can prove, that if the initial gap is say G0, then pull-in phenomena will occur when the displacement is 1/3 of G0. When the gap is 2 by 3, then the pull-in phenomena will be dominating. So that way you can calculate what is C max by C min. You will find the 50% change is capacitance possible by this kind of mechanical tuner. But those mechanical tuner, if you have a 50% change, 3 by 2, that is 1.5, 1 to 1.5, 50% change. So it will boils down to 20% change in the frequency. So somebody has asked me a question, that what is the logical thinking process? Am I going to the wideband? If you can have a tuner which have actually capability of 20% change in the frequency, the potentially it can give me a wideband kind of a frequency tuning. Whereas in case of the normal LC VCO, the frequency tuning is limited to 4-5%, because you have this problem of KVCO. As I mentioned, your phase noise performance would have been worse if you increase your KVCO. So in that way, tell me when time is less. In this way, if you make that structure, we found that is some voltage, and this is some kind of a varactor structure. So you will find this is some kind of a meandering structure, this is the two beam structure, and then we calculated it. This is the optical view of those MEMS varactor, which can replace the conventional chip varactor and so on. And this is, you can find very easily that if you look at a laser Doppler vibrometry, let me see whether it will not work. So I don't have the videos. You can see that these capacitors are actually vibrating out of plane using these excitations. So I can have a beautiful change in its gap because of this changing the voltage. And finally, what I try to see, that I want to see the capacitance change. So that I have done with the capacitance measurement, CV measurement. You see how the capacitance is getting changed. And finally, when it goes to the pull off, it shorted, and suddenly the machine got, because machine has a compliant, immediately it stopped, so current goes down. So, this is the variation of the capacitance of various devices, 6 devices of this capacitance versus frequency. Now, I will give you a concept that substrate plays a very important role in RF design. In RF, the substrate capacitance actually comes into your terminal along with your device capacitance. I am giving a model how to justify that and extract the actual de-embedding or de-embedded capacitors from the device, a case study. So, look at the device. So, this is my device, a capacitors, and this is my substrate, and this is the buried layer, heavily doped buried layer for grounding, and this is the silicon, or this is basically silicon nitride or oxide for dielectric layer. This is the gold one. So, you are interested only about the capacitance between the top and the bottom electrode, yes or no? This is the capacitance for the varactor. Now, you see in the path there is a dielectric cap C2, there is also another cap here C3 with respect to this one, and there is another plot C1. So, when you have touching the probe from probe this one, okay, then how many capacitance are coming in actual? So, you are having basically C0, which is your desired cap, plus all these capacitance together. So, if you look at the expressions to that, okay, then you will find I need a femtofarad capacitor, but there is around 1.9 picofarad capacitors which is coming just as a parasitic substrate capacitance. So, you need to have, that is why I am saying that in order to avoid this, this is the probe stations we have, the where you can measure that one. So, you can actually make, I am giving you tricks that in spite of the device you make a dummy structure, okay, and dummy structure you make the measurements, and that is now you actually subtract that capacitance from your capacitance obtained with the device, so that you are de-embedding the substrate cap and other parasitic capacitance to get the actual capacitance of that. So, if you look at that, you will find that experimentally obtained capacitors theoretically predicted is 1.6 picofarad, experimentally we got 1.47, which is only the test structure, that means without the device. Then if you calculate this one, you can de-embed that one, so you can find a beautiful change in the capacitance, because it is the only change in the capacitance which is coming to your device, which is from 500 femtofarad to 650 or 620 femtofarad. So, that is the requirement which has been imposed on your design. Okay. So, what you find is the capacitance after de-embedding, which give you a much more realistic design, realistic capacitance rather than one. Next one, I am quickly going that next important things coming up, that okay, this is a varactor, then can you make a filter, or I say the clock? Why not you make the clock inside the chip without going to the crystals, because now only part that is remaining in the transceivers is the clock, that is the crystal, and the crystal is bigger size. So, can you make a clock using some kind of a micro machine structure? That can be done by this kind of a resonators. I am quickly giving the approach, that is, there is a circular disc which is being actuated by an RF in, this is a port, input port, this is the output port, and first when the RF in goes and it is biased DC, then it will vibrate at a frequency of the RF in, and then it vibrational energy, mechanical energy, it converted to the RF in the output port, and this will give you the input RF to Rn, but it will act as a resonators. Now, look at here in the resonator characteristics, I am just quickly going. So, these are some of the structure, very exotic structure fabricated by SOI, metal and silicon process, those resonators. This is called the metal resonators, and this is very interesting. It is called thick silicon oxide, that means it is the SOI or silicon on insulator resonators structures, which can be used as a filter, which can be used as a clock generators. Okay? And that finally will give you the kind of quality factor you can achieve. Mind it, dimension of this resonator is only 20 micron into 20 micron, but I am getting quality factor is a measured data is 77.5, and you believe it or not, in SOI I got how much is the resonating? You just check. I got nearly 100 something. Quality factor? Yeah, look at. So this got given me only the structure is 20 micron into 20 micron. This is a resonating structure, and that offers a quality factor at 100. So you can think of it, if you have just a resonator and you can make this crystals, you can replace the crystals and make a very good spectrum response. The quality factor is 1 by q square. So I think that I have given you, this is the few concepts how can make a filter by combining these 3 such resonators in series and making those structure and so on. So, and the kind of packaging that will come later on. So this is not the case of MEMS. So with this, let me end the overall gamut of development of frequency synthesizer. In nutshell, I would say that 3 important characteristics you have to look at a frequency synthesizer is the frequency stability, is the phase noise, and the settling time. Secondly, power consumptions. Please, you can have very good performance, but your power consumption is heavy, 10 milliwatt. Actually, you want to design finally a sub-milliwatt transceivers. So frequency synthesizer being the most power hungry design, think of it the challenge behind you, how to make an frequency synthesizer which consume even less than 1 milliwatt of power. Secondly, that you have extreme critical mixed signal approach. You have those programmable divider, you have those control bead arrays, then finally put together, you have the VCO, their loading effects, you have all this charge pump have their change in the current because of the current mismatch, then you have the programmable current source and so on. So all this design is very, very complicated, but still after achieving lot of things, you still your miles to go, and then you find, okay, let's go to new technology node, that is called the technology developments. So you have those inductors, you have those capacitors incorporated in the CMOS chip, and maybe possible in one day you will get really a sub-milliwatt kind of a frequency synthesizers and at very, very high quality factor. Thank you. So now I will go to the online demonstration of a design of a frequency synthesizer. So whatever you have learned so far, which you have find that there is a gap, hope this gap will be filled with the actual design way. So I will take 1 or 2 questions, then I will at the end I will take all the questions because I find this is very, very important for you.
Sir, these MEMS devices, they are micro machine devices.
Yes.
And our other circuitries in a CMOS flow. So how these two are integrated? Because you said that you want to have this resonator on chip.
Now the TSMC and I have not gone into details because I can also deliver one course on MEMS. The MEMS is actually now being CMOS platform is coming up. IMEC Belgium and TSMC both are offering the technology. What is that is a post CMOS process. So you have your CMOS at the lower level, and then there will be an isolation layer. On the top you have the MEMS. They are interconnected through vias with a silicon carbide layer. So that is how they are integrated. Okay. And I am seeing the newer technology, trends of newer technology. So that's why I am saying that maybe in future MEMS will come up as a resonators, as a filter, as a varactor, or as your I said about the inductor, to improve the performance further and further in terms of power consumptions as well as in the phase noise.
Sir, there are simulators available which integrate the CMOS and the MEMS
that is
process
called
flow.
the MEMS plus process.
MEMS plus process.
MEMS plus process is a Coventor platform.
Coventor platform.
So
is it been used for this?
Yeah.
Acha, it has been used.
What is that MEMS plus? Actually, in a mechanical domain, you are having those spring constant, damping coefficients, mass, resonance frequency, and so on. In case of the electronic circuits, you have say LCR. So, inductor, capacitance, resonance and resonance frequency. MEM plus is giving a transformation from the mechanical domain to the electrical domain. So, whatever be the mechanical structure you have, equivalent transfer function in the electrical domain is being created by the MEMS plus. Then when you have those transfer functions, you can calculate the corresponding lump parameters and feed it to your SPICE model to make your LC design. So, I have done this. So, this is called the interfacing with the MEMS simulators with the standard CMOS tool or the cadence platform. Yeah.
Yeah, in this session, I will not go to the details, transistor level description, as already sir told. So, what I will try to do in this session, that in a very small or nutshell way, I will try to go for a first order or a simplistic way to characterize or to design a integer PLL. Okay? So, as already you came to know that in a standard PLL architecture, there will be a phase frequency detector, then it will go to the charge pump, which will push the charge to the loop filter, and the loop filter output, which is a control voltage, will go to the a voltage control oscillator, and this oscillator voltage will be divided by some factor, and then it will be compared with your actual PFD. So, here the PFD is actually comparing the two frequency as well as phase. So, one of the input is, let us say I am putting F ref, means it is the reference frequency which is coming from the crystal or some other place, and this is the divided down, that is F VCO by N. So, when it is locked, this F VCO by N is equal to F ref. It means that F VCO is equal to N into F ref. So, it acts like a multiplier. So, it means that as if this transfer function or the complete block diagram actually multiply the input reference frequency with the times a factor of n. N is an integer number, let us assume. In the next case, I will go to this particular architecture in a design steps, how I can go for this. Let us just have a few seconds. So, this particular architecture is having the phase frequency detector, which is actually digital logic, and charge pump, it is pushing the current or sinking the current. Loop filter is a filter, standard filter, it could be active filter or passive filter, we generally use for passive filter, and a VCO. So, most of the things which is be controlled by the PFD or phase frequency detector, and it is actually a digital logic. It means that the amplitude of the F VCO by N, here this signal amplitude and this signal amplitude does not matter at the first case. This means that the signal is actually compared digitally, means it is a nonlinear system. So, what I am talking that the system is a nonlinear in terms of the amplitude, but the system could be thought as a linear system in terms of the phase. It means that when there is a phase difference between F ref and the divided frequency, how the PFD will behave and how the charge pump will behave, and then how the control voltage will be generated. This is the control voltage VCTRL. So, in this case, let us think in another way. Let us assume that if there is a delta phase of amount of difference at the input reference frequency and as well as with the divided frequency, I will get some charge pump current of ICP. That means that as long as there is a phase difference of delta phi, I will get a charge pump amount of current, ICP amount of current. Okay? So, sorry, this is not. So, this delta phi is proportional to my charge pump current. So, more is the phase difference, more will be the output voltages. How it affects? Let us say I am having a F reference frequency and I am having a divided down frequency, if there is a phase difference delta phi, so I will get a pulse at the PFD output and again I will get a pulse at the next periodic start. So again I will get a pulse of delta phi width and I will this PLL, basically the PLL will proportionally in this time period it will push some charges or sink some charges from the low filter. So if my charge pump current is a constant current source, so my total current at the filter will be proportional to delta phi. So if you can just assume that this particular waveform, let us say this is the f ref frequency and this is the f VCO by n. If particular waveform is moving right side from the nominal position, so delta phi will increase. So it is the delta phi, then it will be more delta phi and ultimately it will cover the whole time period. So you will get a complete time period of the time, that means the twice phi of the phase angle, where you will get the complete constant current. So I can see that if there is a delta phase difference is twice pi, I will get a constant total current is ICP, because fully it is draining the current. So if I get any other delta phase, for example, I can write that for twice pi phase difference, I will get a constant throughout current is ICP. So for delta phi amount, it should be ICP by twice pi. Okay? So this amount of, this is the gain of the charge pump, and then into delta phi. This is the, yeah. So for delta phi, yeah, sorry, yeah. So the, for the delta phi amount, I will get a amount of current will be ICP by twice pi into delta phi. It's a proportional. I am thinking it is a linear. And then this amount of current will go to the filter. Okay? So let us say assume I am having a filter transfer function, let us say ZF or ZS, let us say, or in frequency domain. So I can say that ICP by twice pi into delta phi into ZS, because this is a unit of current, because this is also unit of phase, this is a phase, so this is a unit of current, multiply the impedance, I will get a control voltage of Vs. And that particular control voltage Vs again multiplied with my K VCO, okay, I will get a frequency. So I will get a frequency which is also dependent on the time. So basically, but I am comparing at the input is at the phase. So basically I have to integrate this frequency output changes with respect to time. So I know that anything integration time will give me a transfer function kind of 1 by s. So actually output phase difference will be Vs into K VCO by S. Okay? So I got three things. So I got a ICP by twice pi into ZS into K VCO by S, and then I have a divider factor is normal integer n. So I have a divider factor of n. So this is a standard first order linear phase transfer function, open loop phase transfer function of a integer PLL. So what is the closed loop transfer function? Hs by 1 plus Hs. Okay? So this is up to clear. So my design steps will start from actually here. Let us first assume that what could be my filter. Of course, the filter could be just a capacitor, or I will not go so much detail because of time. So there is, we generally go for a second order filter. This is actually ZS. So my ICP current will, or ICP by twice phi into delta phi amount of current is flowing from this direction. So what is the ZF? It's easy. It's not that much difficult. It's like just it is just I'm not going for full derivation because it's this is parallel to 1 by C2S is equal to ZS. So this if you simplify, say let us say 1 plus R1 C1 S by SC1 into 1 by SC2 by 1 plus R1 C1 S by SC1 plus 1 by SC2. If you go by this way, finally you will come down in a factor. It's look like that let us say I am just writing the transfer function domain. Where this will be my ZS, where B is nothing but 1 plus C1 by C2. Just you can derive and you can have this. It is not that difficult. And omega Z is 1 by R1 and C1. Okay. So the complete transfer function, and probably if it is multiplied by, then it will be then R1, that is all. So this is a constant term factor of R1, R1 is the resistance factor. So if you multiply it, so with the other factor like ICP by twice pi and all these things, so you will have a complete open loop transfer functions. So the complete open loop transfer function will look like ICP by twice pi and then ZS, that is R1 into 1 plus S omega Z by S plus omega Z 1 plus S by omega P2 into B minus 1 by B into K VCO by S multiplied with 1 by N, multiplied with 1 by N, correct? So out of this, the frequency dependent term, if I just omit, I see that okay, ICP by twice pi into R1 into K VCO divided by N and B minus 1 by B, this I will put a constant term, let us say K, let us say. So this is basically K into something, some S domain transfer function. Okay. So this is the a generic open loop transfer function. Now the question is that what I will do with this? The factor is that let us start with a little another way difficult, another way to describe this. So if this is a transfer function, so you can see that there is a how many? There will be actually it is a third order system, correct? You have there is a 3 poles and 1 zeros. It is a third order systems, and you see that in the filter actually it is a second order. So always mind that whenever your filter order is some n, your total PLL order will be n plus 1. If filter order is 2, your PLL order will be 3. So it is a third order PLL. Okay, because of the K VCO by S, because there is a pole at the 0. This is the most dominating factor which will give you the instability, because you know the pole location at origin will always give the instability, unless and otherwise you are making some with some zeros. So you have that zeros here, and these zeros you have connected through you have implemented through the resistance. So that's why I am not going that details. That's why you are using the R1, that resistance is because to create a 0, so that you will not having a double pole at the origin. If the R1 is 0, you can derive this omega Z will nullify, and ultimately all pole system will be there, and then the system will be unstable. What do you mean by the instability in the PLL? PLL is not a linear system, correct? Already I told you. But in terms of the phase, it is a linear. So what do you mean the instability? Instability means in the phase domain. That means it possible that if you don't design your filter properly with KVCO and all these things, then you might get a phase instability, because PLL is a phase domain linear transfer function. So what will happen, you will see that if my square waveform is f ref and my f VCO by n is f VC, let's say this is the my another input frequency. So this delta phi will be unstable. It means that this delta phi will be, with respect to time, it will change up and down. This is a delta phi. So what does it mean that? It means that your actual waveform after the divide ratio will wander around this common point. So sometimes this waveform will go here, sometimes this waveform will go here. So you will never lock, the VCO cannot lock. VCO will always finding where I have to settle down, and continuously it will go up, means it is not going up, but it is going to the left, right, and it will go continue. But in the transfer function you can see that as I have, if you just go for the derivation of the Hs by 1 plus Hs, you see the term, there is a term, the transfer function will look like a standard well known factor, the denominator. So it is having the, what is called this, damping factor. So it means that after, even also after designing this loop filter, you will still get a wandering of the delta phi, but the amplitude of the delta phi wandering will come down. It means that the in properly designed PLL, your delta phi amount will be come down to 0, and it will settle down by this. Okay? This is a second order control systems, or this is a second order systems generally. So this is the first, this is the thing. But now let us, as it is a transfer function, let us define the phase margin, because there is a phase margin. So phase margin, what you have to do, the transfer function what I have told you or I have derived here, you have to go for the phase domain or the tan inverse domain kind of thing. So the phase will be actually tan inverse omega c by omega z minus tan inverse omega c by omega p2. Omega p2 is the second pole and omega z is the 0. So okay, so if you derive, if you take a derivative of phi m with respect to omega c, you will get that finally the omega c optimum will come, but you have to derive by your own, because I am giving the clue and after that you can derive. The omega c will be generally k into b minus 1 by b approximately, and this omega c can also be represented at optimum phase margin as a square root of omega p2 and omega z. Now what is omega p2? From the transfer function, as we have already derived, so omega z I already told that it is R1 and C1, and omega p2 you will see that it is almost R1 C1 C2 by C1 plus C2. Okay? So if you go this, it means that R1 C1 and then above that C1 plus C2 by C2, that is 1 by R1 C1 into 1 plus C1 by C2 plus 1. So you see this is a B factor, B into 1 by R1 C1. That means B into omega z. So it means that your omega p2 is actually B into omega z, and omega z is equal to 1 by R1 C1, and omega c is equal to omega p2 into omega z. So you have all sufficient information now in your hand. Now let's start about the talking about the real value. The factor is that for the real value, what we have to do, we have to, you again assume that the loop filter is R1 and C1 with parallel a capacitance C2. Why C1 is there? Because C1 is the main filter, Why R1 is there? Because R1 is the zero creating factor, so that the function will be stable. Why C2 will be there? C2 will be there, it is to reduce the ripple at the control voltage. And generally, it's always being followed, the rule of thumb is that C2 generally less than 1/10 of C1. You should remember this to design a PLL, and always you will get a satisfactory result. So, if you have C2 around 1/10 of a C1, then you have a sufficient phase margin as well as ripple. So, now factor is there. So, you know, let us assume that C2 is equal to 1/10 of the C1. So, what is the B factor then? B is equal to 1 plus C1 by C2. So, it is 1 plus 10, 11. So, I got the B. Okay. So, again it means that I got omega P2 is equal to B into omega Z. So, okay, I got that 11 into omega Z, let us assume. Okay. So, I got some factors. Now, let us start about our omega C. What should be my omega C? Omega C is what? Omega C, it is the radian per second, is basically the bandwidth of the loop in terms of radian per second. What do you mean by the bandwidth? Because PLL itself a frequency contains factor, there is everywhere VCO's effect is there. So, out of that which frequency you are talking? It is a frequency on which the delta phi wanders around its nominal point. Okay? So, you want that the wandering of the delta phi or the locking should be done with a specified amount of time, and as well as there will be less ripple at the control voltage. That means that your locking time will dictate what is the actual bandwidth. Okay? So, lower bandwidth means that it is the higher capacitance of the loop filter. So, delta phi cannot change too much, it is a very sluggish. Higher omega C means the loop bandwidth is higher. It means that if there is a slight perturbation or faster perturbation at the F rep, the PLL will act. Are you, this is a real feelings, I will just tell if I get some time.
If you look at the response function, response of any circuits, it is actually inversely proportional to the bandwidth. So, if you have a higher bandwidth, your response will be much faster. So, here is the catch, that how you determine your loop bandwidth. If your loop bandwidth is high, noise will be more, and in that case you have the fast response time. But what I is seeing that the omega C is that, so how do you actually tailor this omega C to have an effective bandwidth as well as the moderate response time?
So, omega C dictates the bandwidth, and as well as omega T dictates the response time. Omega C dictates the my settling time. So, there is a literature. Of course, settling time and omega C relation is not 1-to-1, but the rule of thumb is that your locking time, let us say TL, is approximately 4 by FC. This is published, means it is a older for the third order kind of PLL, but not for the first order or second order. Approximately this equation holds. Okay? So, if I set, let us say I am putting a locking time 4 microsecond, it is for example. Of course, the locking time actually has on 57 microsecond, but let us say 4 microsecond to easy my calculation. So, what could be my FC? 1 megahertz, correct? So, it means that omega C is twice pi into 1 megahertz from this equation, let us say. So, you come to know first from the your locking time, you have to assume this equation. I will give the reference for that, and then you have to calculate what is omega C. Once you find the omega C, you know that omega C is equal to omega P2 into omega Z. Okay? And B factor is how much? 11. Okay? So, and also I know also I know omega p2 is b into omega z. So, if I put that, I will see this will be factor b into omega z. Yes, correct? Just if I put omega p equal to bz, it will be like. So, if I square root of 11, so it means that omega z approximately equal to omega c by 3. If I take the C1 by C2 ratio as 10 by 1, only in that case. If you take higher, you will get a different value, but it is easier here. So, omega z is equal to omega c by 3. So, it means that your zero frequency fz is 1/3 megahertz. Okay? If your FC is 1 megahertz. So, now you have the clue, because you know that omega z is nothing but 1 by R1 and C1. So, now you are coming to the actual closer loop filter characterization. So, you know omega z, from the locking time you know omega c, from there you got the omega z, and omega z is nothing but 1 by R1 and C1. From that R1 and C1 value you might have a clue to calculate, because the loop filter is the most strategic part, but you do not know R1 and as well as C1. Okay? So, what I do, let us take the equation where omega c I have tell that it is almost k into b minus 1 by b. Okay? So, I know this k factor. K's factor is ICP by twice pi into k VCO by n into R1 is equal into multiply b minus 1 by b. Okay? Your b factor is 11. So, b minus 1 is 10 by 11, approximately 1. Okay? And now I need to know charge pump current, I need to know the VCO gain. Now, I am coming to the actual PLL VCO characterization. So, my specification could be in our design, or in our design we have used ICP around 130 microampere. It is just our design. It's, you can think now this is your equations, and now you put your own current value. And our KVCO, as it is not a wireless communication, so we have a KVCO is little higher, because we have to go for a faster jitter capturing, because jitter tolerance some kind of, this is a different thing. Our KVCO was 250 megahertz per volt, and that means that twice pi into 250 10 to the power 6 radian per second per volt. Okay? So, if you put this value, and also n we have, okay. So, there is another specification, of course, for the PLL is required. The first specification, what is your reference frequency, what is the VCO frequency. We have used the FVCO as 5 gigahertz, and we have used the FREF around 125 megahertz. You might ask, why so much high? Because this 125 megahertz is generated from the another PLL, that PLL is called jitter cleaner. I assume that 125 megahertz it is readily available. Okay? For us, it could be 10 megahertz, 1 megahertz also, whatever. And this is my, so what is the n factor? Is, you can see it is a 40, because 40 times of 125 megahertz is equal to 5 gigahertz. So, you know now n is equal to 40. So, you know now the equation of ICP, n KVCO, and b minus 1 by b. Okay? Multiplied R1 is equal to omega c. You know the omega c. Yeah? So, from this equation, this is, let us say, equation number 2. So, I can calculate twice pi of 1 megahertz, correct? My omega c is 1 megahertz. 1 into 10 to the power 6 is equal to 130 microampere by twice pi into 250 into twice pi by n is 40 into R1 into b minus 1 by b. So, it is 10 by 11. So if you calculate, R1 should come around 7.73 kilo ohm. So you got the R1, and you know the second thing, that omega z is equal to 1 by R1 C1, and you know omega z is nothing but 1/3 of megahertz. That means 1/3 into twice pi into 10 to the power 6 radian per second. So you know the R1. So you calculate C1. C1 is around coming from 61.8 picofarad. If you calculate, it will be easy. And what is the C2? I told C2 is 1/10 generally. C2 is 6.18 picofarad. So now I can write down a summary. Summary is like this: my FVCO is 5 gigahertz, my FREF is 125 megahertz, my frequency dividing ratio is 40, my omega c is equal to twice pi into 1 megahertz, correct? And my charge pump current is 130 microampere, and R1, C1, C2 I already know, 7.73 kilo ohm, 61.8 picofarad and 6.18 picofarad. Your design is almost done. So you put a loop filter, put the current for the charge pump for 130 microampere, set the divider ratio by 40, and you should able to settle down with it. And another thing I forgot to remember, that your phi m, I am talking that it is tan inverse omega c by omega z minus tan inverse omega c by omega p2. So when you take a derivations and then you find the maximum phi m phase margin, you get the optimum phase margin after that putting omega c value. So you should get around tan inverse b minus 1 by twice root b. So it comes approximately 53 degree. This is phase margin. So you got a overview, and now I will show the simulation results, but unfortunately PLL simulation will take much time, because
Normally, for any PLL to lock in, it takes 7 days. So if you have two choices, wait for 7 days and or whatever the captured I can show you. So even with very huge computing facilities, 2 to 3 days is required. So even one of my students worked 1 month just to get each nodes of lock-in. So I said that you capture the event and show.
So we have captured some intermediate result in our presentation. We can show that it is a captured view, and of course post layout it will take 7 days to run properly. Yes. Bandwidth of the loop.
Bandwidth, say that. But you said damping?
No, damping you have to calculate from the equation. If you write down the equation, then, but omega c is the bandwidth. Bandwidth where the open loop transfer function magnitude will come down to unity. No, not settling. When you have HS, you have came to know this equation. You take the argument of that, putting S is equal to j omega. Take all these things and make the argument, that is the magnitude value equal to 1.
We have just 10 minutes.
So where the loop gain is becoming 1 or 0 dB, that is this is not a 3 dB bandwidth, it is a cutoff bandwidth for the PLL. So see, this waveform actually tells that whenever there is a phase difference between the reference frequency and VCO divided frequency in one direction, you see that these different colors mean the width of the one of the pulse is increasing, whereas the another is keep on same. So it means that it is a PFD characteristics. Better I will show by this way. So this plot it's showing that when I am just moving around from the 0, that is the when there is a phase difference, it is a when it is a phase difference here 0, and then if I shift my VCO divided by n frequency by left or right, I will see that charge pump and loop filter will generate the voltage in this manner. Of course, this is not much linear, but you see around the locking time it is almost linear. Okay? So, the slope of the curve actually is the PFD and charge pump and loop filter gain. This is meaning that. Okay? So, you have to calculate, but finally you can get also the PFD CP characteristics by this way also. And this is our intermediate result. So, 800 nanosecond till morning, till morning we have seen that it is the control voltage is now going to settle. It is the worst case corner, the slowest corner with highest temperature with full load. It is going to be locked. Yeah. So, we have given for 10 microsecond time, because for the demonstration purpose we put the lowest or the minimum possible settling. These are the test setup. We can see the test setup. Oh.
Yeah, this is test setup. This is the test setup. Here the BGR and here the PLL. Okay. You can see here PLL. This is VCO, divider, PFD. This is charge pump and this is loop filter. It's not clearly visible, but this. Okay. And this is total VCO, 5 gigahertz VCO. Okay. And these are the switches for capacitor tuning capacitance. And this is PFD. This is total 40 divided by 40. So, it's 1 by 2 here, divided by 2 here, divided by 5 here, divided by 2. So, total it's a divided by 40. And this is high speed latch. Okay, for division of 2 you are using. Yeah.
Because it is always burning the current. It is a current logic. It's not CMOS kind of logic. It means that the swing of the voltage is not from the ground to the power supply. The swing of the voltage is halfway around. Like it is, let's say I am having power supply of 1.2 volt. So, CML logic will generally go for 0.6 volt to 1.2 volt. It means if it is a 0.6 volt, it is states as a logic 0. If it is a 1.2 volt, it states as the logic 1. It is a divided by 5. This is all static kind of nature. This means CMOS logic is there. So, these are operating at the lower frequency. As already sir told that when the VCO is having the highest frequency, or sorry, VCO already having the highest frequency like 5 gigahertz, the nearest divider will be the CML kind of technique. And when the divide down, the frequency is coming down, then you can go for the CMOS logic. CMOS logic static current consumption is 0. CML logic static current consumption is of course not 0, it's high, but it will give you higher speed. Higher speed why? Because to go from the 0.6 to 1.2 volt, you have to take the less time, correct? Rather than 0 to 1.2. So that's why it is a much faster logic. This is a charge pump circuit. Actually, it is might be not clearly visible, but charge pump circuit will look like this way. So it look like is a switch, then there is a current source, and then again a current sink, then a switch, then output is the ZF or ZS, the blue filter. Okay. So this is the ICP and this is the charge pump current, and this is the switch 1 and this is the switch 0. This is the VDD. So when this switch is on, SW1, then the current will go, and if the SW0 is off, then the current will ICP will go to the ZS. And when SW0 is on, then current will go from this to the ground. So the loop filter capacitance will be charge and discharge. But the charge pump design, it's actually it's not straightforward, of course, because when you are switching, means making it on and off, if this is a current source, okay, so current source, it means that the transistor would be in the saturation region. And when you make it off and then you try to make it on, it's difficult for a current source to become suddenly go to the in a current source domain. That means the transistor will not go at very fast to the saturation. So I have to go for the current steering logic and all these things. Okay, so of course it's not possible to tell everything about the filter. And this is the loop filter, as I told. See, there is a discharge path I have made, because if something goes wrong, I can reset the loop filter to discharge by manually. And otherwise, this is a second order loop filter.
This is just, we have last night we have done this, just for a demonstration case, but definitely we have a phase noise performance. But this one, as I mentioned, that here the information content is not in the phase, but we are actually making a serializer, deserializer, and we are using it for our large hadron, you know, that FAIR projects, where they have given a very, very stringent specification of the jitter. They say that it will be less than a picosecond jitter. So we are mainly concentrating on this CDR and the the clock recovery circuits, the PLL. Then the jitter performance we are mainly concerned. So here phase noise performance is we have not that way interested. So we make our KVCO that high. But this one which I have said minus 134 dVc hard, where we definitely make the KVCO very, very carefully and making all the waste, so that burning only 2.4 or 2.7 milliwatt power, including the buffer, we got that kind of phase noise.
Is that in relation between phase
I
noise?
have a model for that. Sometime it relates, but don't rely on it that much. I think if you go to the post-Hajimiri model, the cyclostationary, there is a ISF function. Are you aware of that? So occurrence of the noise when it is in the zero crossing or when it is at the trough, the maximum peak point, depending upon what I am saying, that the phase noise and the jitter. Hello, is this working? Oh, so you can see that now. Now it is locked in. So it is done, actually running is done online. So you can see that now it's become stable. So it takes how much time? So last night we have run this program, and now right now we found our thing is lock-in. So what I am saying, that suppose you have this kind of a sinusoidal signals, and now if there is a noise, these are important concepts, right? If there is a noise occurred here and if there is a noise occurred here, which will be more vulnerable? Make your common sense. That when it is at the zero crossing, that will be more vulnerable, we will have more jittery. But whenever it is in the maximum points, it will be less. So you find they have introduced some kind of a weightage factor that is called ISF factors. So impulse sensitivity factor. So that factor has been introduced, that is a gamma, in the expression of the phase noise, that is post Hajimiri expressions. So in that case, you can find out you can predict the phase noise. And if you look at the jitter one, the jitter one comes actually from the thermal noise. There is a contributions to this, but theoretically it can be seen that it is mostly from the mismatch of the GM. That introduces, so both the thermal noise and the mismatch in, like here the charge pump current variation, how it is coming, the charge variation, because of the basically GM mismatch. That will introduce the jittery in that clock, in that cycles. So the question, how I relate the phase noise which is in the frequency domain and which is in the time domain, the jitter, whether we can interpolate that one, that is still a question. So ab initio you can see, okay, there may be an interpolations, but I would say you may predict a wrong results because of that issue, that where the noise is striking your signal, that is important in defining the jitter. Am I clear? So phase noise is something and the jitter is something, but ultimately it reflects one in the frequency domain and the time domain. And I would say that even when you concentrate on improving the jitter performance, you may not get that much of good performance in the phase noise. You do not require actually. You require, or where you are interested more towards the stringent phase noise performance, then jitter is not that important because it's the time domain, so you can take care by the clock management circuits. Clear? Little bit? So ISF function has to come, and that is an indeterminate one. That is called the some kind of a cyclostationary. It's very difficult design actually. Even a simple VCO to phase noise prediction is a very important characteristics. And actually, it is the 17th century's old ideas. If I study when the German clock makers, they have invented that phenomena. Suppose is a pendulum is moving to and fro, right? And your spring is giving the energy so that the pendulum is moving up and down. It's the 17th century. Now the engineers thinking that where the spring will unwind. When the pendulum reaches to the static end, there it will impart the energy, or when it reaches at the middle of it, it will impart the energy. So you understand your jitter phenomena, that you have a periodic thing where you have to strike that where the noise has built up, at the peak or at the center. So if you can draw the conclusions from that watchmaker, you can really start a very interesting physics of that. Probably that might answer to a lot of these things. If you look at how the watchmaker has invented actually in 17th centuries. And definitely there are both options, that suppose the pendulum is at this end and pendulum is here. So if the pendulum is get perturbed here, then what will happen? It will swing and it will go there, right? Or if you energy gives it here, then it will also like this. So perturbations in this side will be more stability of the clock, which one will be the basic thing. So that you have to look into that, and that's the interesting physics actually, clock makers. Am I able to give you some kind of an thinking mind in this approach?
What part is most difficult in this synthesizer? Designing point of view, what part is most difficult in this synthesizer?
My part, I would say that charge pump. Mismatched charge pump is extremely difficult, and spar reductions. Still my third PhD is working only on these spar issues. But problem multifold when I make it frequency synthesizer for fractional L. I have not given you anything on fractional L. My students have got his degree, and I will have publications to that, but that is a much more difficult plane to handle it in the fractional synthesizers. I am talking only about the integer L and how to handle this, but fractional L will be much more difficult, where the charge pump and all the divider, those clocking noises will come into that. It itself is a very interesting mixed signal complex problems. Come on, next question.
Sir, if we increase the order of the filter, what are the difficulties we will face?
Analytical expression, you cannot design it. Unnecessarily, you will generate more number of poles, and then I said that I made you a clue that initially you designed with second order because your VCO acting as an integrator, so that will introduce another order. So it will be 3 orders. But then if you make it third order, it will be fourth order. So that's why I say that happy with up to third order. So far people all have worked with the third order filters. Second and third. Don't increase your third order unnecessarily. Loop bandwidth will be important. What I am trying to say that please select your loop bandwidth 1/10 of the carrier frequency. Okay, and then I would say the in-band noise and out-of-band noise, then you might play, because if you can open the band too much, then that will invite more noise into the systems. So better you play with reduction of the bandwidth, but at the cost of the response time. Am I clear? So you remember I am targeting 20 microsecond settling time, but I end up with 50 because I have to manage my noise. So you can always increase the bandwidth, but all the thermal noise and 1/f noise, definitely it will crop in. So I have to manage this within the limits of the protocol. Am I clear? Because bandwidth and the response time is the inversely proportional to each other.
Okay, thank you, sir.
That's the issue. So don't go unnecessarily to higher order loop filters.
Sir, can I know which platform you are running, whether you are selecting Spectra RF in Cadence or
You are
which is
running
one
it in
of
the Spectra
Spectra RF?
PSS analysis and phase noise analysis are there, and be very patient. It will take lot of time. So I am giving you a caution that when the lock-in things, you can actually take 14, 18, 20, 40 nodes. Don't look at all the nodes, okay? You just identify 3, 4, 5, 10 nodes, and then your settling time or the simulation time will be less. And better you use an additional memory. And I have also tried with GPU to improve my simulation time, but still 3 days is required.
Thank you, sir.
And there is another caution, don't get frustrated. 1 month you get the lock-in time something, next run there will be a difference. Some differences will be there, but that will be an appreciation. Those are the practical guy or industry guy, they know that it depends upon that time. Lot of in the simulation itself, there will be some variation in the locking time if you carry, say, first phase of, second phase, third phase, like that. Yeah, so now the summary of the results. So it's an online work. So I should thank my student.
Okay. Now is the complete PLL.
Yeah.
It is VCO, it's divider, then it is PFD, it's charge pump, it's loop filter. Here I will show you the locking phenomena. Here the locking, the control voltage.
Yeah. So let's see the control voltage.
Yeah, it's almost locking.
So no more swing up, your control voltage is leveled. So you understand?
Actually, it will take another 2 to 3 microseconds. Now it's 1.7 microsecond. If it will means at 4 microsecond, it's almost stable. So it will take another 10 to 15 hours.
10 to 15 hours.
Okay. So next is you want to see the divider output.
Yeah,
Means
divider.
So
Just zoom it. Yeah. So what is the frequency? You just
yeah, our reference frequency is 125 megahertz. It is also 125 megahertz. You can see.
So you understand that from 5 gigahertz, it is divided by how much?
See, it's almost 8.000061 nanosecond. That means 1 by 800 is 125 megahertz.
125. So it is going to
8.00006.
Yeah.
It's almost log.
So you understand the divider, right?
And I am giving the comparison of reference and divider.
Yeah, so go to that. So we are now comparing with, at any instant of time, comparison of the reference frequency which is coming from the crystal and also from the divide by frequency. You look at here, go to the, yeah.
See,
How much?
almost overlap.
So you can see there is
Just
almost overlap, so it is locked in. You can see a little bit zooming up. Make it yellow and deep blue, white or what is? Yeah, white will be fine. So clear? Now it is the divide by frequency and the, so you can see the locked conditions. So you can find the control voltage flatten ups and my frequency and the phase is becoming locked. So you are having the same profile.
And next thing is the frequency, 5 gigahertz frequency I want to show you.
So you see the frequency, that is the free running frequency of the VCO. Let's go to the VCO mode.
Started here.
So oscillation builds up.
Just see the how it builds up.
Yeah, so you can see how the oscillation starts and then it's actually stabilized, and just show the amplitude as well as the frequency. Just one, zoom it.
Swing is around 1 volts, 995 millivolts.
So around 1 volt swing,
Our
peak to
supply
peak.
voltage is 1.2 volt.
So you are almost rail to rail swing. Okay, almost rail to rail swing. That will drive my mixing, or
Yeah,
this
it's
case,
almost 200 means it's 5 gigahertz, 200 picosecond.
which one is 200? So you can find out the the time period is 200 picosecond. So it is almost 5 gigahertz. So that is the free running frequency of the oscillators. So I hope that now you have confidence in the design, how to design, what are the basic philosophy behind it, how to simulate, what has to be taken into
Okay.
it, and how to compare. Thank you all.